In this lecture, we are going to discuss about the correlation. Correlation is basically a statistical measure expressing the strength and direction of a relationship between two or more variables, indicating how they change together. That is the basic definition, how we can perform the correlation, or how we can say what is the correlation, meaning, or you can say in a more simple word that correlation of two signals is a measure of similarity between the signals. It ranges from -1 to 1, where the values closer to 1 or -1 indicate a stronger or weaker connection of the correlations. Mathematically, you can represent the correlation using these equations. R tau is equals to integral from -infinity to infinity x1t multiplied by x2t minus tau. So that is the representation of correlation between two signals, where x1 is the one signal and x2 is the shifted version of the second signal. There are two types of autocorrelation and the cross correlation. What is autocorrelation? As the name auto, so it means that it is the measure of similarity between the signal and its shifted version. Like you can say R1 tau. So 1 basically is the signal itself, and 1 again the shifted version of the signal. So that is why it is represented R11. If you consider a complex signal xt of finite energy, then the autocorrelation function is given by these equations. R11 tau is equals to integral, where the upper limit is infinity and the lower limit is -infinity. X multiplied by complex conjugate of x t minus tau, like that is the shifted version of signal itself. For real signal, we can write as R11 tau is equals to the integral x t multiplied by the shifted version of x with itself. For autocorrelation, we can define the measure of match, similarity, relatedness, or coherence between the signals. Like there are many different words that you can use for the autocorrelation. The first one is the match. You can be asked that how the signals are matched, like what is the percentage that the signal match, or what is the percentage of similarity between the two signals or between the same signals, what is the relatedness of the signal, or what is the coherence between the signals. All these words have the same meaning, that is the correlations. Second type is the cross correlation. So it means that the cross correlation is the measure of similarity between two different signals, as the name cross. So that is why it is the measure of similarity between two different signals, and we can write mathematically R1 2, where R1 is the one signal and 2 is the second signal. You can also define it like it is a measure of similarity between one signal and the time delayed version of other signal. So consider two complex signal x1t and x2t, then the cross correlation is given by these functions. Like R1t tau is equals to integral, where the upper limit is infinity and the lower limit is -infinity, x1t, and the complex conjugate of the shifted version of the second signal x2 steric t minus tau d tau. Or you can write like this x1 t minus tau x2 steric t dt. Like here the shifted version of the first signal is the multiplied with the complex conjugate of the second signal. Or you can write like this R21. So it means that the complex conjugate of the first signal multiplied with the shifted version of the second signal. Or you can write like this, the complex conjugate of the shifted version of first signal multiplied by the second signal. So all these four equations you can use for the cross correlation, for like the similarity between signal 1 and 2, or the similarity between signal 2 and 1. So the name you can say that is the cross correlation. We have an example where we can calculate the average power if the signal power spectral density is given. Like you can use this mathematical formula, P is equals to integral, where the upper limit is infinity and the lower limit is -infinity, and the spectral density of the signal. S of f d of f. Like if the graph of the signal is given like this, you can see S of f is the power spectral density, and on the x-axis frequency is given, and it varies, the signal varies from -4 to 4, where it has a value of like the amplitude of the signal from -4 to -2 is 2, and the amplitude of the signal from -2 to 2 is 4. So we can calculate the average power of that given signal using this formula. Like we can write P is equals to integral, where the limit is from -4 to 4, because the signal varies from -4 to 4, everywhere else there is a no signal, and the spectral density of the signal. So we can say that, okay, the spectral density of the signal from -4 to -2 is 2, plus the spectral density of the signal from -2 to 2 is 4, as you can see from this graph. Similarly, and the spectral density from 2 to 4 is 2, like you can see from this graph, 2 to 4 it is 2. So you can calculate the integral of each integration, like 2 is constant and the integral is f. So if you insert the upper limit and the lower limit, similarly if you take the integral of this part and insert the upper limit and the lower limit, similarly the integral of this, and then after inserting the upper limit and the lower limit, you can calculate the average power, which is equals to 24 watt. So we are getting the power by integrating the power spectral density, and similarly we can get energy by integrating the energy spectral density. So there is another example. A filter has input xt is equals to e raised to power minus t ut, and the impulse response h of t is equals to e raised to power minus 2t ut, and you are asked to calculate the energy spectral density of the output. So we know that the output energy spectral density is equals to the square of the modulus of h of w multiplied by input energy spectral density, and this is the impulse response of the signal in frequency domain. So the spectral density of the signal is equals to the square of the spectrum, or you can write the input spectral density of the signal is equals to x of omega whole square. So here we are given x of t, the signal in time domain, and we can calculate the signal in the frequency domain. So like we know the relation, that is e raised to power at ut is equals to 1 over a plus j omega, and similarly we can write x omega is equals to 1 over 1 plus j omega, and its amplitude, we know that to calculate the amplitude the formula is a square plus b square, and here a is 1 and b is omega, so that is why square of 1 is 1 and square of omega is omega square. So that is the amplitude of the frequency domain signal. So similarly you can calculate the impulse response h of omega, so that is you can use the Fourier transform of h of t. So using the same formula we can write h of omega is equals to 1 over 2 plus j omega, because if you see the h of t, here a is 2, and that is why, so you are given here 2, and the remaining is j omega, and if you take the amplitude of the signal, so you can say that, okay, amplitude of the signal is a square plus b square. A is 2, 2 square is 4, omega is b, so that is omega square, and then after that you can calculate the square. So if you take the square and the under root will cancel each other, and then using the values in equation 1 we can, and then you can calculate the output energy spectral density, that is equals to square of the modulus of the impulse response multiplied by the input energy spectral density, and then if you multiply them together, the answer is 4 plus omega square multiplied by 1 plus omega square.